Hello. Yeah, I think I'm audible. Yes. Welcome all to the Dealing with Materials Data Collection, Analysis, and Interpretation assignment number 11. So, this assignment is all about discussing about the design of experiments. So, right till now we have we are dealing with statistical analysis after we get the data. But this is quite different. So here we will be discussing how to conduct an experiment to get a meaningful data out of it. Like like if we have only fixed resources, it is not like the resources are infinite so that we can do a number of experiments. For example, for testing, like I know everyone is metallurgist. Most of them are metallurgists or strength of material people here. So you might be aware of testing sample. So hardly we can do at least means maximum 3 to 4, or at most there are 3 to 4 specimens, not more than that. So there is a limit for testing capabilities and resources. So hence, like we have to plan the experiment carefully to assess all the factors in the sense the inputs or the factors which affects the result. So we have to consider all of them and we have to carefully plan the experiment. So for that, this particular assignment as well as the lectures, whatever you might have seen, will be helpful, especially if you are going into the field of research and development or research or analysis of the large big data. So there it will be like very particularly it will be useful. So let's move on to the topics directly. So when it comes to design of experiments, what is this design of experiment? So design of experiment is a systematic method for studying how multiple factors affects the key outcomes. Key outcome may be different things. For example, if I'm mixing a different alloying element, the key output, how does the different alloying element affect the mechanical properties or the hardness or the corrosion resistance. So everything matters. So that is like key outcomes are affected by the alloying elements. Just a minute, just a second. Someone may the class itu kalau itu later now. Sorry for the interruption. So yeah, let's continue. So DOE gives a roadmap for efficient experimentation. As I discussed, we have only fixed resources to do the experiment. Hence, it should be efficient in a way that we should study all the factors which influences the outcome without neglecting any critical factors. But at the same time, the number of experiments should not be very high. So why it is important, as we discussed, it saves time, it minimizes the trial and error time. Then it saves resources, as I discussed, it maximizes the data gain from a fewer experiments. It provides insights. So it can uncovers the hidden relationships. For example, how it can give us an insight about how the hardness and strength are related, how the corrosion resistance and surface wear resistances related. So all those things it can give an insight. With the minimal experiments, we can extract out of a lot of relationships. So for that, the design of experiment will be effective. So before moving further, we should understand the terminologies which we generally use in the design of experiments. So the commonly, if you just open any design of experiment, the two terminology which flashes is factors and responses. Factors are nothing but these are the variables which can control the outcome. So, for example, like in case of any testing or testing, if the temperature can affect the mechanical properties. Then if you go for time also can affect because morning the temperature will be different, afternoon the temperature will be different. So actually time and temperature are like interaction time, they interact each other. Then ingredients like composition can also affect the mechanical properties or chemical properties. So yeah, so these are the factors which the variables which can affect or control the output. So responses are the outcomes which we want to measure. For example, the product quality, yield, or efficiency, yield strength, mechanical properties such as hardness, creep rupture, like everything comes into the responses. How the response with respect to the different factors. Okay, so these are all the two. These two are the very important terminologies which we are going to use so often in this context. Yeah. So, what is the goal of the design of experiment? That is a major thing which is very important, right? So, the goal is to understand how factors impact the responses and how we can optimize the process or product based on this understanding. So, after understanding how the factor affects the response, we can do modifications or optimization in that, and we can improvise the product or understanding of about the product. Okay, that is our goal. So moving further, what is the procedure involved in design of experiment? So when we say design of experiment, first we should know what are the procedures. So first we will define the objectives. So what do we want to achieve? Example, like improvement in the strength of the material or improvement in the corrosion resistance. So these are the objectives. So first we will set an objective, what we want to achieve. Then we will identify the factors. As we discussed, factors are the things which control the outcome. So what factors might influence the outcome? For example, temperature, pressure, time, chemical composition, everything. So all those things can affect the factors. So factors should be carefully identified. Then we have to choose the design. So this is the new part which we are going to discuss now. So the design means in which way you want to analyze or design the experiments, design of experiment. So there are many ways to do that. We will be discussing one by one. And in upcoming slide, we will be discussing why DOE is important before going on to all those things. Okay. So yeah. This determines which experiments to conduct. So design of after choosing the design, you will know which experiments we have to conduct, or which are all the critical experiments which you have to conduct, or what all the experiments are totally available. All those tools will be clearly obtained from the design of experiment. So step four is executing the plan. So how we execute the plan? First, we conduct the experiments based on the chosen design. Then each experiment tests a specific combination of factors. So first we'll conduct experiment based on the chosen design. Then each experiment tests a specific combination of factors. Like sometimes we will be discussing about how the carbon and the nickel influences the mechanical property or yield strength or carbon and molybdenum, how they affect the properties like that. We will see for the specific combination of factors. So by that we execute the plan. Then we collect the data and record results of each combination. Use statistical tool to analyze the data. So and then interpreting the data, like that is what we are doing from since the starting of this course. We have collected the data. Now we are interpreting the data using statistical analysis, which reveals the relationships. Then identify the significant factors and interactions. So significant factors, how we identify whether using the hypothesis testing, whether it has an effect or not, we analyze, and if it has effect, then they are significant factors. So with all these understandings, we can go on to optimize. Okay. Okay, so with this procedure, we will generally we do the design of experiments. Okay. Before that, why design of experiment is required? Like before design of experiment, what people are doing. So that is what we are going to see. So before design of experiment, what generally people will do is a trial and error method. So they will trial different parameters and see how it affects the how the factors responses to the given input. For example, um, say we want to determine the optimal temperature and time setting, it will maximize the yield through experiments. For that, generally what we do is like we conduct a trial at starting values. Like we arbitrary do this. We don't have any rationale to select this. So to variables and record the yield. For example, in trial one, we are selecting the temperature to be 50 degrees Celsius and time to be 24 seconds. In that, what is the yield we will see. Then from this, we'll record a yield. We set it as a benchmark. Then what we will do is like adjust one or both values based on our results. So we have got a result. So what we will do is like we will change the variables and see. For example, we keep the time as constant like 24 seconds and we increase the temperature to 120 degrees Celsius. So when we do this increment, we will see how the yield is being affected. So here we can see when we increase the temperature from 50 degrees Celsius to 120 degrees Celsius, we can clearly observe the yield is increasing. So now what we are going to do is like we are going to increase the time as well, or we are going to decrease the time. So in that way, we can see how the yield is getting affected. So what we are going to do is like we keep 24 seconds, then 20 seconds and 12 seconds as the three different time variables, and we are changing the temperature as well. So one is like lower circuit, which is 50. So for 50 and 24 combination, the yield we know already 53.86. We increase it to 120/24, for that we know 60.48. And then we decrease the temperature to 100, and we decrease the time also. So for that 100 temperature Celsius and 20 seconds, we can see there's a further increase in the yield. So now what we are doing is like again we are decreasing the temperature with keeping the time as constant. So we are going to 80 and 20 and see there is not much change in the yield. So next what we are doing is like changing the temperature has not negligible or like not positive effect on the yield. So what we are doing, we are keeping the temperature as 100 degrees Celsius itself, and we are further decreasing the time. When we do that, we can see the yield as 87.7. Then we thought that okay, temperature should, if it is high, then the yield might be high. So we increased it 120, 12. That combination didn't give higher than the previous one, like fifth experiment, fifth trial. Hence, we say the fifth trial has the highest yield, and that is the optimized parameter. Optimized parameter is 100 degrees Celsius and 12 seconds or 12 minutes time. Okay, that is how you optimize. Here it doesn't have any proper structure. It is inefficient, unstructured, like without if you don't know if you don't know the understanding behind this process, then like we can't even tell like whether this is optimized or not. And it is unlikely to find the optimal set of conditions across two or more factors. For example, if we have more factors, uh, then there is no structure to carry out the experiment. We will be like arbitrarily changing the things, and we will be doing unnecessary lot of experiments, and we will be ending up using a lot of resources as well as time. So this was the earlier method which people were using. Then what they did is like they started using one factor at a time method, OFAT method. So in this method, what will happen is like we will change the value of one factor, then we will measure the response, then repeat the process with another factor. So here, as name specifies, we will be attacking or we will be discussing only one factor at a time. So we can understand the response of the another factor. Okay, so uh, for example, in the same experiment whatever we were discussing before, uh, where we are up to optimize the temperature and time to maximize the yield. This is how the YFAT experiment, one factor at a time method, will be carried out. So what we will do is like we will start with the temperature, find the temperature resulting in highest yield. So for that, we fix the time. We fix the time to be like 4 hours or 10 hours, like that, and we change the temperature and see how the yield is getting affected. So actually, what is happening is that with increase in temperature, as we have seen, with increase in temperature, we can see there's an increase in yield, but it is not like monotonically increasing. Up to certain point, like 90 degrees Celsius, it is increasing or giving the maximum yield, and it starts to decrease. So you can see clearly compared to the previous method, that is the trial and error method, where we don't have any idea how the yield is going to be yield is going to vary with respect to temperature. Here we have got a profile to see like how the temperature affects the yield, and we know where the maximum yield is being achieved. So this one helps in understanding like the highest yield between 50 and 120 degrees Celsius, and how the temperature yield varies with respect to temperature. So next is we'll do the second experiment. We're keeping the temperature constant at 90 degrees Celsius because that is where we have got the maximum yield, and we are going to vary the time between 4 and 24 hours. We start with 4 hours, we increase it with 4 increment up to 24 hours. And so, see, in that case, we could see the optimal yield is being achieved at the optimal yield is being achieved at 12 hours of time. So 90 degrees Celsius is the optimal temperature, and with the optimal temperature, fixing the temperature should be 90 degrees Celsius. We are varying the time, and we can see 12 hours is the time where we get the highest yield. So according to the one factor at a time method, now we have established a relationship between the yield and time and yield and temperature, and we have obtained the optimal parameters with the same data sets whatever we already had. So with that we are clear that 90 degrees Celsius and time of 12 hours is the optimal parameters where we get the maximum yield. So what is the optimal what if the optimal temperature time setting look like this? So if you see this curve, you can see the optimal value lies between uh, lies somewhere in the upper circuit, like nearly close to 90, which is like not within our text experiment range. So in that case, we will be missing out acquiring the optimal temperature and time setting based on the previous one factor dynamics experiments. So in those cases, OFAT will fail. So how to and also we here they doesn't yeah. Here it doesn't establish any interaction between the time and the temperature, all those things. It just tells factors independently and their impact on the yield. So these are the drawbacks of this OFND experiment. So to counter this drawback, we are moving on to the next robust method is carefully planned methods called design of experiments. So with the disadvantages of trial and error, the optimum range might be missing out. We are moving on to the design of experiment. In design of experiment, we will be establishing a window of potential experimental region. You can see here. So this is the experimental region, the shaded region. So we will be taking out the we'll be experimenting within this region so that we won't be missing out any parameters while achieving the optimum parameters. So there are different methods to do this. Like there are a lot of methods actually available in this available, and it's also evolving. Like you might know it might be like something around six methods I have which I have stated here, but there might be several other methods also which is being currently used. So the out of this here, as per whatever discussion happened in the course, like we are only going to discuss two important methods. That is called full factorial design and fractional factorial method. So then apart from that, we have Takuchi method, and then response surface method, then central composite design method, and the box layout method, design method. So all these methods are there, but we are now just going to limit ourselves with respect to factorial design, and we will see with examples how we can use them with methodological examples also. Okay. Hello. Yeah. So let's move on to the full factorial design. So full factorial design, as name suggests, factorial means it explores the all combinations possible. So so it examines all the possible combinations of factors at all levels. Then let's provide the information on main effects and interactions. So when studying all possible combination of factors, and when we have moderate number of factors and levels, we use the full factorial design. If we have many levels and many factors, then this process might be like highly expensive and as well as complicated to conduct. So, for example, it is possible in case of testing a metal alloy with three elements like iron, carbon, and nickel for optimum strength. So, if you want to test it, what we can do is generally do is there are three C2 ways to select two alloys and strength. Like we cannot be like when we have three different elements, which is being brought into this context, we have to study with the different combinations. For that, first we will study with addition of two elements alone. So in that case, we are in how many ways we can choose two elements out of three elements. So we can choose it in 3C2 way. So 3C2 means it is 3 factorial divided by 2 factorial into n minus 1 factorial, which is 1 factorial. So this is like 3 into 2 factorial divided by 2 factorial. So we can cancel out 2 factorial, and we three ways we can choose two elements. So that is here you can see iron plus carbon, iron plus nickel, then carbon plus nickel. This is 3. And one way we can 3C3 is possible in one way. So that is iron, carbon, and nickel. This is one possibility. So totally four possible combinations of combinations can be performed in this the full factor revision. So now if you see the factors are like easy. Only we had three factors. So now the combination whatever we have got is only four. It's like imagine if you have like a higher number of factors of two different levels means the number of experiments will be like almost doubling and tripling. So to minimize that only, like we'll be using one more technique called fractional factorial design. So we'll discuss it like subsequent studies. So let's now explore the full factorial design first. Yeah, in full factorial design, the experiment with two factors and each factor has two values. For example, temperature and time are the two factors, and it has two values. That is one varies from 50.4 to 120. The other varies from 4 to 24. It's the same problem whatever we have seen before, right? How the temperature and time affects. So that we are going to see in terms of factorial experiment. So what we are doing is here it is very robust. Why I say robust is we also replicate the factorial experiment for at least two times. See how the impact is, whether there is any variation in the experiment. So that will also be ensuring in the case of this DOE, this is full factorial experiment. Well, what we do is like we take the extremities, that is 2, 1, 120. 0.24, then yeah, sorry, 120 and 4, then 54. So it will time varies from 50 to 120. Yeah, temperature varies from 50 to 120, and then time varies from 4 to 24 hours. Using this extreme values, we construct a region within which we can carry out the experiments. So we will be repeating every experiment twice to get reliable data. So the repeatability will eliminate the possible errors, and we run all possible combinations of factor levels in random. So we do it in random because if we do it in a particular sequence, then the sequence itself might have an impact like on the material property. Hence, we do it in random and then average of the effect of working variables. So we do it like 50, 24, 124, then 120, 24, 54. So like that we do it in random, which each set having two values. So in that way, we will establish a relationship, like how the temperature and time varies, and how does it result in the yield. So this is like one way of conducting the full factorial design. So we have explained with only two factors, time, temperature, and time. If it has multiple factors, say like if you have factors of like three factors or four factors, uh, then number of experiments will be like 2 times k. 2 is a level. Like sometimes people write this like L times scale. Number of levels and k is the number of factors. So if you have two levels, say high and low, and number of factors like 3 means if k is equal to 3 means we have to do 8 experiments. If k is equal to 4 means we have to do 16 experiments. If k is equal to 5, then it will become 32 experiments. So it will be keep on doubling with just one number increase in the k, which means the factor. So in that case, we will be performing fractional factorial design. So what is fractional factorial design? So fractional factorial designs are a useful method for screening the experiments or when sample sizes are limited. So like either when sample sizes are limited or if you have a method to screen the experiments, like uh, by that you will be able to identify the critical experiments and only perform that experiments. Critical experiment means there will be few factors which critically affects the resulting properties. So, and sometimes if we don't have enough resources for full factorial design also, we go with the fractional factorial design and number of factors become large as I told. With just to increase in one factor, the experiment number of experiments doubles. So if the number of factors become large, then the fractional factorial design will be opted. So as I told, generally if it has two levels like high and low or maximum minimum, then will be and k factors resulting in 2 power k experiments. For example, suppose if you are designing a new car, there are and we identify 9 factors. So if I identify the factor is the first method, one of the first preliminary methods of POE, with each factor having two levels. So, for example, the 9 factors can be like engine size, number of cylinders, the amount of drag which the car experiences, the weight of the vehicle, whether the transmission is automatic or manual, what is the shape of the car, what is the tire size and suspension configuration, gas tank size, everything. So these are the 9 factors. If I want to analyze all these factors, then I have to do 2 to the power 9 experiments. 2 to the power 9 years, it will be like 128 to 56. 5 total experiments. That will be like huge actually. So in that case, what we do is like what we have. You say we have only resources for 2 to the power 6 trials. It is 64 trials. So in that case, we have to drop out few factors, considering that they might not be critically important factors. For example, tire might not be a very critical factor here, provided like if you are traveling in a city right. In that case, the gas tank size also doesn't matter because gas tank size is not a critical factor. Since if you are riding within the city, we can fill the gas or petrol or at the required interval. Then drag. So especially when you are driving in city, the drag means it is aerodynamic drag. The the velocity is very low that it doesn't influence the aerodynamic drag at all. So apart from that, aesthetically the shape is very important. Suspension is important for bumpy roads because especially city roads are like bumpy. Then whether the automatic or manual is very important. Weight affects the mileage, so weight is also an impacting factor. The number of cylinders affects the power, and engine size also affects the power. So we can rule out certain factors like tire shape, tire size, drag, and gas tank size, and we can minimize the number of trials. So as you can see from here, like it needs a prior experience and proper knowledge about the factors for the subject to eliminate out the unwanted factors. So hence the fraction of the 2 power 9 full factorial design will be used for the DOE of fractional factorial design. And if you have, if for metallurgical example, we can use this. If you have many alloying elements, it is impractical to test every combination. For example, if you take a super alloy, it has 9 to 10 elements. So if you want to conduct different experiments for each factor or each factor here represents each element, then we have to conduct 2 to the power 9 experiments or 2 to the power 8 experiments, which is like 256 or 5 experiments. It is huge. We cannot afford to do such elaborated testing for all the samples. Hence, what we can do is like we can choose five alloying elements which are critical for mechanical property, and we can perform test on those particular alloying elements. For in this case, if we have five alloying elements, let's boil down to even this. We have five alloying elements like iron, carbon, nickel, chromium, manganese. This must be a steel. So with this combination, if you want to do, how many tests we have to do? Say the number of factors were like one, two, three, four, five. So five factors are there. We can use the levels like high, then low, or the two levels. So 2 power 5 experiments. 2 power 5 experiment means so 8. So 32 experiments have to be conducted in this case. But this is like too much because like we know only iron, carbon and nickel influence, iron, carbon, nickel and iron, carbon, chromium influences the strength of the material. The manganese might not be a very critical factor. Just hypothetically, I'm talking, not actually discussing the realistic impact of the manganese. Just I'm telling you that iron, carbon, nickel, and iron, carbon, chromium might influence the mechanical properties. So he just do those two alone and we compare the results. Or see the response. In other words, with the same elements, if I want to do the um, uh, s- testing for the strength in that case, or start testing for new oxidation resistance. In that case, amount of chromium, amount of nickel, and amount of chromium and amount of nickel has higher influence on mechanical corrosive resistance compared to carbon or manganese and means carbon or manganese. Hence, we can drop out those factors and concentrate more on chromium and nickel. So in this way, we can screen unwanted parameters and we can factors and we can focus more on the factors which has a critical impact. So as we discussed, when to go for a fractional factorial method or full factorial, if your motivation is to identify very few significant factors as discussed before, like from trivial screening, then the fractional factorial design is efficient and alternative to the full factorial design. As I discussed, if you are going to discuss about oxidation, this is an important factor. Like important factors are such as uh, iron, chromium, and nickel can be considered, while the manganese and carbon can be avoided, hypothetically speaking. So, why does it? Why it is very important? Because the fractional factorial design could save time and resource, it helps to identify the important factors quickly. Because like if you do full factorial, it takes a lot of time and resource. So the fractional factorial design is quick, it saves time, it saves resources, and it helps us to identify the factors, influencing factors very quickly. Then insight, provide information on key factors without listing everything. So as we have ruled out certain factors, now we will be focusing more on the key factors, not the unnecessary factors. And this is for screening and narrowing down. For this, we need a special knowledge or the subject knowledge to this sense. It is narrowing down needs further step. So this is the construction of matrix. As I told, if you have two levels, that is +1 and -1. These are the two levels. And factors such as three factors. A, B, C. So total number of experiments is 2 to the power 3. It is 8. So you can see combinations 1, 2, 3, 4, 5, 6, 7, and 8. So under each level, how many you will be doing? Here we are studying the interaction also. Without interaction, the number of experiments will be less. But here we are studying the interactions between AB, AC, and then BC, then ABC together. I is the factor which is like which is used for fitting, like that's called orthogonal matrix or the orthogonal matrix. So in this case, fractional factorial design, we can eliminate or we can only choose the very important factors while eliminating the unimportant factors and only do those particular experiments. Okay, so till now we have discussed the basics of or the base for the DOU. Now I think we are ready to launch and explore further into the problems and understanding. So which of the following statement is correct about the uncontrollable factors of the experiment? So uncontrollable factors of the experiment means uh, those are the factors which control is not in our hands. For example, let's see the uh, example for heat treatment process. Temperature of the furnace can be controlled by us. Duration of heating can be controlled by us, and quenching medium can be controlled by us. But uncontrollable variables are like initial microstructure we cannot control because it differs from the lot. If supplier has a whole different lot or like each lot has a variability in microstructure, then it is very difficult to control the initial microstructure. So that is uncontrollable variable. Then ambient air conditions. For example, if you do in the morning, the temperature, ambient temperature might be different. If you do in the night, the ambient temperature might be different. So it changes. And then means air conditions is not only temperature, but humidity also changes. And varying in the humidity affects the corrosive property, corrosion resistance properties. And then chemical composition. So chemical composition differs from one supplier to another supplier. We will be continuously procuring the product from one supplier or we will be procuring from any other supplier. So it may vary based on the supplier. Then size and shape of the sample also different differs based on the supplier. So in this case, the response variables might be like testing hardness, yield and dimension, and the elongation. Okay. So as per the question, what are the uncontrollable factors? You see the first option, the factors which doesn't affect the response. If something which doesn't affect the response, it is not at all a factor. So this is not the correct thing as per the debugging. A factor which affects the response can be controlled. Then it is not uncontrollable, right? Which can be things which something is under control, means it is uncontrolled behavior. So the factors were this is called factor. Okay. Then a factor varies a normal distribution like random. Yes, like some factors are like occurs with just random, so which cannot be controlled. And factors which can be increased or decreased as per the which cannot be increased or decreased as per the occur. Certain factors like as I discussed, the ambient air condition. When we don't have any air conditioner, then it is difficult to as control it. Yeah. So the answer for this is C and D. So moving on to the next question. Suppose an experiment need to be designed to study the effect of three factors, that is temperature, pressure, and catalyst concentration on a chemical reaction. The output response is the rate of chemical reaction if both temperature and pressure have an interaction. So if both temperature and pressure have an interaction, like OFAT, one factor at a time is the correct method to do the experiment. So in one, as we discussed before, one factor at a time does is like just varying one factor at a time by keeping another factors constant. So which means like it is not discussing about any of the interaction at all. Hence, the both temperature and pressure have an interaction. So one factor at a time is not a correct method. So it is false. Then which is the correct method? So in that case, we should go for more comprehensive experimental design methods such as factorial design, full factorial design, or Takeuchi method. There are several methods which discusses the interaction. So we should go with those methods. Okay. So moving on to the third question. Just give me a 1 minute break. Let me have water. In third question, according to the Sir R.A. Fisher, what are the basic principles of DOE, design of experiments? So, according to the Dr. Fisher, there are three basic principles of randomization, replication, and blocking. So, these are all like repetition is repeating the experiment. These are all good for design of experiments, but not the major thing. And sequence factorial design is method of DOE. And then sequentiality is like is an actually issue. We should not do sequencing, rather we should go for randomization. So answer is randomization, replication, model. Okay, let's discuss what is randomization, what is replication, and model. So randomization means instead of following a particular order or sequence while doing an experiment, we go for random order. So in that way, we can we can eliminate the error, random error. So that is randomization. Here you can see it is a standard order where we are doing the experiment in the given of one particular sequence. For going for when we are going to replicate the same experiment again or repeat it again, that time we should go for different order so that we can check whether we are getting the same response for different response. So that is randomization, and replication is like doing the same experiment again should be getting similar results. Means it should not be entirely different because of the randomness. And then let's move on to blocking. Blocking is another basic principle where we will have multiple blocks or multiple batches of samples, and one batch to another batch, this sample might have a variation in the properties. To account that, we should be like considering testing from different blocks or different batches. So that is called blocking. So in this way, we can remove the experimental errors. So these are the three answers to the given question. Analysis with application and plot. So moving on to the fourth question. In the fourth question, consider three factors: temperature, pressure, and catalyst concentration. And each factor like has two levels. Higher per factor. Only pressure and temperature has two level interaction. What will be the size of the terminal developments? So as per this, all the three has two level interaction. So then it should have had a um, three one factor three one factor, that is pressure, temperature, and catalyst reaction. And that is concentration. That is degree of freedom is three for one factor. For two factors in normal case, it should be like three. It is AB, BC, so it is like two level interaction. And then for orthogonality, like the when we use five, we use one degree of freedom. So for the constant. So three for the one level, then degree of freedom. It's like degree of freedom for the two second level interaction or two level interaction is one as per the question. Then one for constant of constant. So basically we have 5 degrees of freedom. So the minimum number of experiment which we can do is 2 power n. So that is 2 power 3 here. Because 2 power 2 means only 4 will come. The next one possible is 2 power 3. So 8 experiment of 2 power 3 as is the size of the orthogonal matrix. Okay, this is the answer for the fourth question. So moving on to the fifth question. Which of the following statements is or correct about the design of ice cream? Is used to develop a new process. This may not be correct because we start a new process and we think for optimizing it. So it's not about start to develop a new process. It's about optimizing. So second point is correct. We used to optimize the process parameter. Then it is used to study the effect of individual process parameters on the response. So It is not right. Like when you want to optimize the progress parameter, then you should know what is the impact of the effect on the effect on the factors on the response. So that is also thought. It is used to for this. It is used to study the interaction between the independent variable on response. So yeah, it is used to study the interaction between two independent variables. For example, if a carbon and chromium has an influence on the mechanical properties. So what is the addition? What is the interaction between carbon and chromium? It can form shear M23C6 bondage. That of the C6 bond, right? And they can reduce the property carbon concentration when they are mixed together. So that also how to be studied. Hence, it is also used to study the interaction between the independent variables on the response. Interaction between the so these are the three answers like B, C, and D. So before moving on to the next question, we have to understand one more thing. Like so far we have designed and we have discussed it now, VOE in terms of mathematics. But graphically also VOE means a lot. So one such tool is a main effect plot. So the main effect plot in VOE is used to visualize the effect of each factor on the response variables while averaging over the average of other factors. So each line in the main effect plot, for example, there is a main effect plot represents a different factor. So this represents different factor, this represents different factor, this represents different factor. The slope of each line indicates the magnitude of work. The negative slope means of the negative impact. Positive slope is positive impact. If it is having higher value means it has higher impact. Higher slope is higher impact. Higher magnitude of slope is higher magnitude of impact. So slope as the magnitude. And not only that, if you see there are two different factors, like greater than 1 and greater than 2. If it is flat, then there is no effect. No effect and no interaction. But in other case, the greater than A and greater than 1 and greater than 2 has an effect. But they don't have any interaction. Like when they are added to the liquid, they are increasing the temperature because of the exothermic reaction. But there is no interaction between the detergent A and detergent. But if you see in the third one, there is a significant interaction. How we are saying significant interaction? Because when we increase the concentration of the cleanliness of say detergent one, the cleanliness of detergent two is decreased, which makes it is turning out to be hot. When it is hot, the cleanliness is low, but when detergent one is hot, the cleanliness is high. So it has an interaction, and they will have a crossover. So visually we can work the magnitude as well as the interaction. So with this understanding, we should go on to the sixth question. Graphic analysis of design the main effect law gives an idea of how each factor affects the response at each level. The one factor, if one of the input is most impactful to the response, the slope of the represented slope like the line representing this factor and the main effect law can only be negative, it's not correct, can only be positive. So also not correct. It can be positive as well as negative. It is only the how steepest is the line that tells the magnitude of the impact. Okay. So when it is all about the steepness of the curve. So increase in impact. So user response, excellent impact. Moving on to the seventh question. The two-factorial design is carried out. That's they are carried out DO equal two-factorial integration. The effect of three factors based on the response is being studied. The below figures are representative of the interactive form, like how the reality interacts. So here you can see from this plot, they are asking what conversion will be. Here, with respect to A, with the addition of B and C, how they interact, how the response rate is. That's what we have this problem. For the given A, the beneficial the low B and high B has no interaction. Like B has C. After doing B has no interaction. So that is correct. Because they don't have any crossover links. So they don't have any interaction. But in case of A and C, you can see there is some interaction between each other. So after A and C acid money. So B and C are the correct answer. Okay. With this, our discussion on assignments as well as the topic is that. But if you have further doubts, this session is out for our audience. Ready for the discussion right now. If you have doubts, you can either text me or you can directly ask. So confirmation.